Hi, my name is Anton and I work at Azul, and I also lead the project CRaC, which stands for Coordinated Restored Checkpoint. Today I'll make a small introduction to the project and I will describe each of these terms. But first, why after all of these years Java still has startup and warm-up problems there? We may see this as a simple example. Although for a human the program is very clear kind of print a line, call a method, and the method should print another line. JVM actually sees this in another way. JVM explores your program class by class. So first we'll certainly execute the first line, then we'll get to the invoke bytecode, and we'll have to search for the class service. Since it's not loaded, we have to call another special piece of Java code that is called class loader, and its job is to provide definitions of the bytecodes for that class by name. Bytecodes can come from the file system, for example, from a Java file. They can be loaded from network, or class loader may even generate bytecodes on these requests. And this decision where to get bytecodes, it's solely solely in the logic of class loader. And the class loader could be implemented in standard library or in your application itself. Then, since JVM does not control from where these bytecodes come, JVM needs to ensure they are well formed. JVM runs verification procedure, and only if bytecodes are fine, we can finally allocate some native memory, layout bytecode for execution. And now, since the service class has a static initializer section, it should be run first before we could get to the target method. Graphically, we can think about this as a timeline. At some point all classes related to your application are loaded, so your application can do something useful. This could also involve loading some classes in advance, or it could also mean that classes are loaded lazily as a part of processing another kind of request that was not seen before by this application. But let's say that at some point that the startup point, your application now finally get into processing user requests and do something useful. Meanwhile, with this process, there is a JIT compiler that competes for CPU resource with application threads. JIT cannot compile all the code because it probably would be a waste of time. So instead, JIT compiles only some hotspots, and there are chances that during startup transition, JIT will compile only utility methods of the standard library and not application logic itself. But once startup is complete and your application transitions to processing some real workload, JIT finally could compile the relevant code, and now your application is getting executing faster and faster. At some point, this JIT compiler activity ramps down, and your performance of application becomes pretty flat. And there, at that point, let's say that warm-up is complete. The part of the problem with the warm-up and startup is that the biggest source of performance improvement, the JIT compiler, should compile some code. But this code is not available from the very start. It's getting loaded dynamically by class loading. And JIT usually don't have some foreseeing procedure to imagine what bytecodes will be loaded next. So it always works with the current state of JVM and bytecodes. In general, this is pretty hard problem to deal, but we know kind of an interesting and very successful approach in this area, that is ahead of time compilation. And Graal compiler, Graal native image is example of the implementation of an ahead of time compilation. Graal relies on the closed world assumption, that is, that it should be able to understand the program from the very start till the very end. And that means all classes that will be loaded are known in advance in a build time. And then, since the whole code is known, now LT compiler now has a chance to optimize the whole program as it is. And since this is done in the build time, we can spend much more time on optimizing than is possible for JIT compiler. So a part of the computation is moved from the runtime by the build time, and this could be seen as a kind of an implementation of a very general approach called time-space trade-off. So instead of lengthy and costly computations for the bytecodes, we pre-compute them in the build time and store results of this class loading and resulting compilations in the image. But some of the computation still has to be done in runtime as a part of your application logic. But the good thing is that once these small remaining things are done, this startup completed point is also a point where warm-up is complete. Just because for the rest of the execution, LT compiler generates a native code that does not need warming up. What's interesting is that time-space trade-off is not the time-space trade-off can be implemented in this way. In Project CRaC, we explore another way that is called checkpoint and restore. The idea is following. During the build time or deploy time or actual runtime in your production, we run our application as usual. And at some point we declare a checkpoint that is associated with creating an image with the complete state of the JVM that will hold all the Java heap objects that were created at the moment, all the Java threads and their states, also role classes and JIT codes that were generated before that point. And this image can be restored into another working Java instance. And once restore is complete, we may think about this as another instance startup and warm-up complete. Warm-up complete at this point because you are in control where to do checkpoint. So if checkpoint is created after warm-up is completed in the original instance, restored instance will be also warmed up. An interesting thing, how long does it take to restore an instance? For that, we created a set of microservices implemented with a popular framework like a Spring Boot, Micronaut, and so on, and Quarkus, and measured how long does it take to start a microservice on regular OpenJDK. We have created a checkpoint at some point and measured the time to restore. And the result is this. So actually it takes only a few tens of milliseconds to restore. And that means that you have another working Java instance in a few tens milliseconds. And it's the same old Java instance that you had before checkpoint. And also an interesting property is that time to restore does not depend on the amount of computations that were done before checkpoint. Only what's important is the size of the image. And you may imagine for microservices not that big. Speaking about runtime performance, this is a warm-up curve for a Quarkus framework, example built with a Quarkus. And here we see that at first each request was executed slowly, but over the time execution gets faster and faster until in around 200 to 20k requests the curve became a line, and that means that each request executes in a constant time, and this continues until up 100k requests. We have created checkpoint at this point actually, and once we have restored the instance, the curve looks like this. So we may see that the curve is a line from the very start. So the restored instance is warmed up from the very start, and the slope of this line is the same as it was around 100k requests. So the performance is the same as if you have properly warmed up during 30 seconds before, but you get this immediately. If you're interested in the total runtime of these instances for the simple microservice, we are saving around 5 seconds in executing 100k requests. Yeah, with this with this encouraging results, we need to discuss the last but the major part of the project CRaC, that is coordination. It wouldn't be very useful if a single instance, if a single image could be restored only once, or for example, if instances could be restored only sequentially. That is, for example, as if it would be forbidden to restore a single instance twice at the same time. But for microservice, this is not very straightforward, because they would conflict on the listening port. So what can we do in this to solve this? The idea of coordination is to provide a notion of checkpoint and restore to the application. That is, to allow the application to sense checkpoint and restore and react on these events. So, for example, a restored instance may find changes in environment that have happened since the checkpoint. For example, a microservice that is a part of a bigger system could register to orchestrator or a work distributor. And also, another important example is that application may decide that the state at the moment is not very suited to be checkpointed. That is, for example, suppose the application is doing transition from one phase to another, and doing checkpoint in the transition is not useful, just because every restored instance would be doing the remaining part of the transition. And in this case, application may decide that checkpoint should not happen at the moment, and there is a way for checkpoint for application to abort checkpoint, and probably a proper handling for this is actually to try a checkpoint once again after some time passed, for example after a second. Actually, from JVM point of view, we must say that some application states are not suited for checkpoint by inspecting the JVM state. If we find an open file handler or network connection, we abort checkpoint. Why? Because having this connection, for us it's a kind of a link with the external world that we cannot control. And if the application has such kind of link, it means that something in the external world that we cannot control may change and prevent application running correctly on restore. So we abort checkpoint if we have if we find some this links with external world, And since the application may know about checkpoint, we require that application should not have any kind of links with external world by closing these links in a checkpoint phase. That is, the idea of coordination is that application and JVM work together to ensure that the image makes sense, and also that the image will be always possible to restore, and that the image is robust to the changes that may happen in the bigger environment to the JVM. Otherwise, if that is not satisfied, the image is just not created. Actually, for our examples, we have added coordination code. So all results were obtained with small pieces of restoring code to handle those environmental changes. And interesting is that the size of that code is not that big. So, for example, the coordination code in Quarkus that handle HTTP endpoint, cross checkpoint and restore fits the only one slide. What's missing there is a kind of dropping a few of jar caches. We think this is a proper way to implement coordination code, to implement this code in the framework and not in the application. Because suppose you have an application that is built with some sort of framework. If your framework has a coordination code, your application gets this support of the CRaC for free. You don't need to do anything. And this is probably the common way how applications are written. They do not manage resources themselves. They rely on libraries, frameworks, and so on. So that's why we hope that CRAC API is possible and will be widespread because it's small and is natural to add to the place where it should belong. But for now, until it's not happened, you can always play with our versions of frameworks that were modified with coordination code. Bare bones of API are pretty simple. So there is a resource interface that has two methods that will be called before checkpoint and after restore. Before checkpoint can throw a Java exception that will abort checkpoint, as we discussed. And so after restore may throw the exception as well. And all exceptions in this case will be collected and reported in a single place where you could log them, handle them, like a main method of the main class throwing a set of exceptions when it could not start. And all that remains is to register this object implementing methods into CRaC subsystem. And this API is implemented in OpenJDK Project CRaC. In this case, OpenJDK project means kind of a development branch without any commitment for when this feature will be ready and when it will be delivered in which version of JDK. But there are EA builds of CRaC JDK that are based on JDK 17. Another major part of the project is organization on GitHub. There you will find third-party projects that were modified with coordination code, which includes a set of frameworks we have discussed, and a set of Apache libraries and projects. So, for example, there is Tomcat servlet container that also can start in 50 milliseconds. Then it will pick up servlets and will start serving them, as you would expect. And there are also a set of examples which we may which we would like to extend and extending over time. For example, a few of them are using some different approach. So, for example, Jetty is more kind of library, so the coordination is implemented in the example itself. You may think about Jetty example as the simplest example for the CRaC, for using CRAC API. And some of them, like a Spring Boot, do not require any changes in Spring Boot itself, but it's enough to make a change in POM XML and to choose a version of HTTP web server that has that coordination implemented. And suppose, for example, that you'd like to play with CRAC API, but you don't want to tie your project to the yet not released Java version. In this, for this case, there is a project that's called CRaC. The idea is to provide a wrapper to the JDK CRAC API that will allow your application to build on any JDK you'd like. You don't have to change your to change the JDK you use to build your application. And then CRaC is also a runtime dependency. So once you start your application, CRaC finds a proper implementation of CRAC API in the JDK you are running on. So if it's EA build, fine, you'll get the CRaC as you would probably suppose. But if you're running on a regular OpenJDK release, all CRaC calls will do just nothing, but your application will be running without any problem. So you can play with CRaC API by just adding a single dependency to your, for example, Maven or Graal project. So that's probably all. Please refer to the links for more details, open a GitHub issue or initiate any discussion on mail list, or just drop me an email. Thank you for attention.